Let's look at some architectures that we can have and the implications of using those architectures, right? So we can talk about superscalar, and we can talk about VLIW, very large instruction word architectures, right? Performance can be improved by faster clock, right? We can have a faster clock frequency which would decrease the time period, but we can't increase the clock speed beyond a certain point, and we have to look at the delays that are there when setting up the clock speed. Then, as discussed before, we can have pipelining, which can be used to slice up instruction into stages and the overlapping the stages, like we discussed previously, that at this point in time instruction 1 was in phase fetch operands, instruction 2 was in decode, and instruction 3 was being fetched. So these three stages were overlapped by instructions 1, 2 and 3, 1 being in stage this one, second instruction being in stage this, and third instruction being in stage this. So this is parallelism. Pipelining results in parallelism. And we can also have multiple ALUs that support more than one instruction stream. So separate instruction pipelines can be there, in which instructions can be executed in parallel. So some processors like the Pentium and the Core have used this architecture to speed up instruction execution. So we can talk about the superscalar architecture. Scalar are the non-vector operations, and superscalar basically fetches instructions in batches and executes as many as possible. Basically, when we talk about the superscalar architecture, the idea about fetching of the instruction, and the idea about execution of the instruction, and the idea about which instructions could be executed in parallel and which instructions would be executed in sequential manner is taken during runtime. So superscalar is a runtime arrangement, because in the runtime arrangement all these decisions are made during runtime. So extra hardware is required to make these decisions, and thus the hardware would try to find out which instructions could be executed in parallel, and so on and so forth. So as it says, may require extensive hardware to detect independent instructions or instructions that can be executed in parallel. On the other hand, VLIW, very large instruction word, makes use of a compile time arrangement to make these decisions. What do we mean? That all those decisions about independent instructions and sequential instructions are done during compilation at compile time. So the compilation might take a little while longer to complete, but the result would be that minimal manipulation would be involved at runtime. So VLIW is basically a compile time approach to finding the parallel instructions and grouping them together, while superscalar is the runtime arrangement for making those kinds of decisions. So very large instruction word compilers might have a big instruction word size, in which, for example, instruction 1 and instruction 2 might be included together in a single instruction word, hence the term very large instruction word, and in 1 and in 2 could be executed in parallel independently. So there's a lot of interest and growth in the VLIW architecture. Now, talking from the memory point of view or the hardware point of view, we have got the two memory architectures. The first one is the Princeton, and Princeton requires fewer memory wires, because in the Princeton architecture the program memory and data memory are together. They are not different. They are not differentiated. So the same memory could store the program, and the same memory could store the data. And the same single bus would be used to access both program and data. So this single bus is accessed. So because of this single bus, what happens? The architecture of the system is very easy and simple. On the other hand, Howard architecture differentiates between program memory and data memory. So program memory is accessed by a separate bus dedicated to the program memory, and data memory is accessed by a separate bus dedicated to data memory. So what is the result of these separate buses? Simultaneous program and data memory access. So in this bus, only a program memory or a data memory could be accessed at one time. But over here, since we have parallel paths, parallel buses, so program memory and data memory could be accessed together. So of course this means high throughput arrangement. But the Harvard architecture would be complex. It would require more complex circuits, and that would include the cost of the processor. So usually DSP chips mostly use the Harvard architecture to increase the performance of the processor. And many of the desktop microprocessors use the Princeton architecture. Then we have the concept of the cache memory, and as we discussed before, memory access may be slow. So what do? We produce a bridge in the form of a cache between the fast microprocessor and the slower memory device. And in general and in very brief terms, the cache holds a copy of part of the memory. Since cache is small, it cannot hold the whole memory. It holds only part of the small memory size in the cache. And then we have the concept of the hits and the misses. So what is the concept of a cache hit? And what is the concept of a cache miss? Any student? So after that we look at the programmer's view. So the idea is that the programmer doesn't need detailed understanding of architecture, right? So if we have a programmer that doesn't know to have the detailed understanding of the architecture, instead needs to know what instructions can be executed. In fact, when we talk even about assembly language, what are the two things that the programmer must know? We discussed this previously, right? The first one is programming model. And what is basically a programming model? Programming model is a set of all the registers or the internal registers of the microprocessor that can be modified by using software or computer programs. And what is the second knowledge that an assembly programmer needs to have? An assembly programmer needs to have the understanding and the full knowledge about the instruction set. Instruction set of a particular processor. And what is an instruction set? It is a complete encyclopedia of instructions. So that has been summarized. If you move to a high level language, we did not even know to have any knowledge about programming model or instruction set. In a high level language, we only need to have the knowledge of the high level language itself, the commands that can be executed, right? So what are the two levels of instructions? The basic lowest level is the assembly level, which was this thing that I talked about earlier. Since we are very close to the machine in the assembly language, we need to have the idea about the programming model and the instruction set. But as far as this another level, high level is concerned, we have the structured languages, for example C, C++, Java, etc. So most development today is done using structured languages. Why? because of high productivity and ease of use. Assembly language is good. Assembly language is the most efficient language, but assembly language is a little hard to understand and learn. On the other hand, these languages are simpler. But we also need to do some assembly language programming whatsoever. So if we want to increase the performance of the programs, we might code the slow part of our structured language program using the assembly language. This is called assembly language interfacing, and many of the languages support assembly language interfacing. But if we want to have high performance software, for example drivers, which communicates with or controls drives or hardware, we often need to have assembly level for that. So as far as the drivers are concerned, especially the GPU drivers for your graphics cards, they are always programmed using the lowest level, which is the assembly level for that particular device. So a little discussion about assembly language instructions, and basically what does this instruction consist of? Opcode, operand 1, operand 2, the second instruction opcode, operand 1, operand 2, etc. So basically what is the instruction set? Defines the legal set of instructions for that processor, and the instructions might be grouped into the following groups: data transfer instructions, which include instructions from memory to register transfer, register transfer, memory to IO, register to IO, etc. We might also have arithmetic and logical instructions that move through the ALU in back. And we also have branch instructions or control transfer of control instructions, which determine the next program counter value when not just the logical next program counter value. So basically branching or decision making is done in these kinds of instructions. So let's look at a simple trivial instruction set. This is basically the assembly language instruction, the first byte and the second byte, and these are the type of operation that are performed, right? So move rn comma direct, which is a direct addressing mode instruction. So memory contents of this address location are transferred into register Rn. Then we have move direct comma Rn. This is the opposite of the first one. The contents of register Rn are moved into the address that is specified in this particular instruction. Move at the rate Rn comma Rm. Right. So what does happen in that? Register M value is assigned to the memory contents is specified by register Rn. So whatever is the contents of register Rn, the memory location that is addressed by that contents of register Rn, the value of Rm is moved to those. Then we have the immediate addressing mode instruction, move Rn comma percentage immediate, pound sign immediate. So what is basically the immediate value is transferred into the register Rn. And as we know that immediate addressing mode instructions are the fastest instructions to execute. Register to register instruction or register to immediate instruction are the fastest instructions. Then we have the ALU instruction, add Rn comma Rm, right? The sum of Rn plus Rm, the contents of Rn and Rm are added and the result is produced in Rn. Similarly, subtraction of Rn comma Rm, so the subtraction of Rn minus Rm is produced into the memory location Rn. Then we have the jump if 0 Rn comma relative, this is the branch instruction. Jump if 0, which register Rn. If Rn the value of 0, then we move jump. And where do we jump? The relative value is added to the program counter to create the new program counter value. So this is just an example of a simple trivial instruction set. Now we can look at the addressing modes examples. The first one is immediate. So what does the operand field contain? Operand field contains the actual data. So we get the data directly from the operand field. In register direct, the operand field is a register address. We go to that particular register and get the data. What happens in register indirect? Register indirect, in the operand field specified a register address, but that register address does not contain the data. It contains the address of the data. So we go to that memory address to finally get the data. What about direct? In the direct addressing mode, operand field contains the memory address. We directly go to that memory address and get the data. And what is the indirect? Or more importantly and more properly, memory indirect. In the memory indirect operation, the operand field contains the memory address. We go to that memory address which contains another memory address. So after that, accessing the memory address, the actual data is contained in this particular memory address. So we go to over here to get the address. So we have first memory access and we have second memory access. So memory indirect is the slowest addressing mode because it involves two memory accesses, one over here and the other is over here to finally get the data. More better option is a register indirect, because over here we get the address from a register file and then we access the data by using one memory access. In direct memory address also we have one memory access which contains the data. So we can have now a look at some sample programs. One is the C program, right? Total equals 0. We have a loop which begins 10 and continues till I is not equal to 0, and we have the incrementing of total by I, right, which is the value of I, right? So it has been converted into this assembly language program. We can see that a small number of lines of C program results in a large number of lines for the assembly program. So the steps are there. 0 is loaded into R0, 10 is loaded into R1, and 1 is loaded into R2, and 0 is loaded into R3. So we have this loop over here, jump if 0, R1, comma, next. If R1 is 0, we move to this thing. So R1 is initially 10. So we come over here, we add R0 and R1, and we subtract R2 from R1. R1 is the loop counter variable 10. We subtract R2 which is 1 from it, so we actually execute I minus minus. So if jump of if 0 R3 comma loop, right? So if R3 is 0, we go to this particular loop. Since R3 is 0, we'll go to this particular loop, right? And over here, if R1 is becomes 0, we'll move over here. So in this way we are executing this particular loop. So this is how the things are done. Some other examples can be considered. If you want to carry out these examples, you go ahead and code these examples using this particular assembly language model. Now let's look at some programmers considerations. The first is program and data memory space. Embedded processors often are very limited. So embedded system processors are very limited in terms of program and data memory space. For example, 64K program memory, 256 bytes of RAM, right? They might be expandable, that might not be expandable. So you must work in a very constrained environment when you are working on embedded processors. So you have to code very efficiently, and the tools are also over here that work very efficiently. Another consideration is registers. How many registers are there? But basically having registers is basically a concern, direct concern for assembly language programmers. So one of the golden rules for assembly language programming is to use registers as much as you can, right? So code your algorithm so that everything is basically done using registers. Input, output, IO ports, how to communicate with external signals. That comes under the category of ports. So every embedded system has got ports that can be accessed, that might be 8-bit ports, 16-bit ports, and so on. Then we also have the concept of interrupts. Interrupts allow a system to operate. An interrupt is just like an example of a telephone bell. So when a call comes, you are alerted by the ringing of the bell that the call is coming, right? You don't need to look at the phone every time and find out if someone is calling you. So we talk about interrupts, and when we talk about interrupts, we also talk about the call level depth of interrupts. Well, call level depth basically applies to interrupts as well as general subroutine processing. So since call level depth is controlled by the stack, call and return instructions are working on the stack. So the amount of stack determines the call level depth. More stack you have, more call level depth. Less stack you have, less call level depth. We can now analyze the microprocessor architecture, and we can have a microprocessor architecture overview. So if we are using a particular microprocessor, it's a good time to review its architecture. So we can look at the architecture of a particular microprocessor. An example of having a parallel port driver, right? We can have the information about the direction of the pins of the parallel port. So output pins can be assigned to an output device like LED, and input pin can be assigned to a device like a switch. So these days we don't use these parallel ports and serial ports as they are. We use them in the form of virtual COM ports or VCP, right? So basically we have this parallel port over here, right, and this parallel port over here interacts with the chip. That is one of the companies that sells this chip is the FTDI. So this parallel port communicates the parallel protocol to the FTDI chip, and FTDI converts it to a USB, and so that your system can be connected. This system can be connected to a USB port of your PC for this communication, right? So any kind of IO devices according to the scheme of the parallel port can be accessed properly. Further example of the parallel port has been given. This is basically assembly language coding, and we are using the assembly language coding to look at the position of the switch, and based on the position of the switch we are changing the status of an LED pin. So I would advise you to please read this and have a general discussion about it. So after that we move towards the operating system. And what is basically the operating system? Operating system is the optional software layer providing low-level services to a program application. And what are the tasks? File management, disk access, keyboard display interfacing, scheduling multiple programs, program makes function calls to the operating system. So this is basically the idea.